Okay, Astronomy 10. Let's do another one of these. Hope everyone is safe, doing well. And today we're gonna do cosmology, all right? So cosmology, Wikipedia, is a branch of astronomy concerned with the studies of the origin and evolution of the universe from Big Bang to today and on to the future. That's what we're gonna do today. So from the beginning, what it's doing now, what's going to happen when it all ends, right? Not a bad day. We're going to do all that. You bet. All right. We can do it. Not a problem. So let's get rid of this thing. And we'll go to this picture here. We'll talk about the Big Bang. You've probably all heard the word the Big Bang, right? So last time we talked about that Hubble discovered that the universe was expanding, right? And then he had a meeting himself, Albert Einstein and a Jesuit priest, and they were able to convince Einstein that indeed the universe was expanding. This was in the 1920s. Prior to that, they thought it was static, and there's all kinds of theories. How is that possible? Because gravity should be pulling it all in and stuff. But Hubble showed that not only is it not going to contract because of gravity, it's actually expanding, right? So picture that they've measured all kinds of galaxies, right? All these galaxies really far away. We talked about last time we can measure the velocity, the speed at which they're going. We can measure, their direction. So we've measured all these galaxies, and we know that they're going away. They're moving away. And say you had like a movie of that, a video of that. Well, what would happen if you ran it backwards, right? I mean, if you had a movie of a car, going down the road, right? Well, if you ran it backwards, the car would be going backwards, it'd be going this way, and you'd be able to tell where the car came from, right? If you're able to follow it. If you're able to follow the movie all the way back to the beginning, you can see where it came from. Well, galaxies, you could see the velocity that the galaxies are going now. You can see the direction that they're going. The direction is away. They're all going away from each other. Now the close ones are coming towards us, right? I said Andromeda is coming, but I'm talking about on the big scale. On the big scale, on average, all the galaxies are moving away. Near each other, yeah, they can collide and stuff like that. But in the big picture, where there's thousands of galaxies are involved, on average, they're all moving away from each other. So if you were to calculate that speed, and then run it backwards, well, they're all going this way. So let's just say, what happens if they were instead going the other way, same speeds? Well, they would all come into each other. Well, what if you ran those calculations and you'd be able to tell that, like, at what point are they all going to come together? Well, they've done that. It's about 13.7 billion years ago. There's some controversy to that number. Somewhere between 13.7 and 14, maybe 0.1 billion years, around there, is how old the universe is. The universe itself. So the universe is everything there is, everything there isn't, right? That's what the universe is. So it's between 13.7 and 14.1 billion years. On the test, 13.7. We'll go with that number. There's a couple of different ways to measure that, but we're going to go with that. But yeah, so we can see where they're all going now, right? We can measure. We can do that now. It's measurements. See, measurements aren't something that, oh, this is just your idea or your opinion. No, we've measured it. Astronomers, you can go out there, you can measure this. So it's a measured quantity. So you know where they're going now, right? So it's a simple thing to say, well, where do they come from? Well, just run those calculations backwards. Well, they're all going to come together And when are they going to come together? It's about 13.7 billion years from now, right? And they call that the Big Bang. Yeah, there's a lot of strange names in astronomy, right? We're kind of used to that. Because guys will say something, or the astronomers will say something in the hallway they're talking, and then the name sticks. Happens all the time. Right? They used to make fun of that name, but yeah, that's the way it is. So here's the thing. There was a lot of controversy. There's a lot of astronomers saying, well, you need evidence. You know, you can't just, so you have that, but you need more. You need evidence. You need to be able to measure something. And they said, well, if you could measure, so there should be, if there was a Big Bang, so it was like, so what the Big Bang was, the theory is all the galaxies, everything known in the universe was all it came from one very condensed, very dense area. And then, for reasons that still aren't understood, all that stuff just expanded. They call that the Big Bang. Now, there should be evidence of that expansion. Let me just check the camera. Make sure that I'm rolling here. Okay, it says I'm rolling, so I hope it's rolling. All right. So, what evidence should there be? Well, if there was a huge explosion, there should, those photons, right, from those early days, they should still be out there. Remember, when we look at a distant galaxy that's maybe 1 billion light years away, so you're looking through a telescope, right? That photon of energy comes, goes through the telescope, goes through your lens, goes into the back of your eye, hits the rods and cones. There's enough energy in that photon that it causes a chemical reaction in your head, and then your brain interpreted the chemical reaction. We call that seeing. So that galaxy, so far away and so long ago, has sent energy that caused a chemical reaction in your head. So how about that, right? So photons, unless they hit something like your head and you killed it, you killed the photon, good job, right? It's been traveling for billions of years. But so photons, unless they hit something, they're just going. They'll keep going, right? There's a galaxy out there, it's sending its light out. Our sun sends out light. If there's nothing that hits it, those things just keep going, keep going. So there should be, those photons should exist from the early Big Bang. Just like photons from any other thing happen, right? They exist. Unless they hit something, they're going. So there should be lots of these photons out there, right? And guess what? There is. They can see them. So here's just a couple of, here's a couple of guys in the 60s. They did some measurements. And at first they weren't sure what it is. They were just making these huge. These are telescopes that work at a certain wavelength. We're used to that, right? We study different types of telescopes. So it's sort of like a big horn, but the photons go in and then they go down, and there's amplifiers down here. Well, using this, they were scanning, and wherever they looked in the sky, they had what at the time they thought was some kind of noise, some kind of buzz, right? They weren't sure what it is. Eventually, what they realized is they were looking at the Big Bang. But a Big Bang, you can't just look at some noise and say, well, that's, you know, that proves that that's the Big Bang, that was the origin of the universe. No, it would have a certain shape. So it wasn't until many years later when they were able to measure the shape. I'm going to get to what that shape is. That was the evidence that showed that the Big Bang was a reality. So remember I said there was controversy. People are saying, well, there could be other reasons why the universe is expanding. There could be other reasons for a lot of this. They said, but if that background radiation that you're seeing, that background radiation, that these guys discovered, it was in the microwave region. Remember we talked about light earlier in the semester. Go review that if you don't remember that. They said, well, it should look like, because the early universe would have been very dense. Very dense. Now the universe is spread out. There's galaxies all over. There's a lot of empty space between. But the early universe would have been very dense. Because it was very dense, and when the Big Bang started, it would have started expanding. There was at some point where there wasn't light. We wouldn't have evidence. But eventually there was a point where there would be light. This was a point during the expansion, and then at that point, those photons are available and should still be in space. But remember what we talked about earlier. We talked about black bodies, right? We talked about black bodies. Remember, if you heat a horseshoe, it'll start glowing. It'll be hot, but then eventually you'll be able to see it'll be red. Then it'll become orange and yellow, right, all the way to blue, or then it'll melt. So remember, a black body has that characteristic shape. Well, they said, well, the Big Bang, remember, stars act like black bodies, because although they're balls of gas, they're very dense. So the surface is, it's a dense gas, kind of like molten lava. You see Hawaii, the lava flows into the ocean. It's a rock, but it's liquid, but it's dense, right? So the sun, although it's gas, it's kind of like lava-y, where it's a very dense hot gas. So it acts like a black body. They said, well, the early universe would have been the same way. It would have been a dense, compressed gas, so it should have the shape of a black body. Remember, a black body has a characteristic shape, right? This here is wavelengths. Remember, we went all over this. I went over this. Go to my videos on spectra, right? At the end of the spectra videos, I talk about black bodies, right? Here's intensity, right? How much power, how bright are those? Is that energy, right? And this is wavelength. Remember, wavelengths start at, like, radio waves, and then they go all the way through to gamma rays, right? X-rays. It has this characteristic shape. Well, so what they had to do, now we're not able to measure that from the ground, because our atmosphere is, in a way, these signals are too weak. But they built a spacecraft. It was called COBE. C-O-B-E, right? COBE spacecraft. In fact, the chief scientist on that mission, he's now the chief scientist for the James Webb Space Telescope. We talked about that earlier in the semester. In fact, I showed a video on it and everything. But, so they launched that spacecraft, and what they were able to do was measure the cosmic microwave background radiation, but they were able to measure it, across a spectrum, right? Across a band of spectra. And they plotted the data, and guess what it looked like? Well, it looked like a black body. That was evidence. It's measurable. So the Big Bang isn't somebody's opinion, or some this, or some crazy idea. No. It's measured. Measured is different than just an idea. It's something that you can measure it again, right? Measurements matter. So if you measure this background radiation, it looks like a black body. Now, it's very cold. So what happens is, it's in the microwaves. The reason it's in the microwaves is the universe is expanding. Back when these waves first formed, they would have been very hot. Very hot. But because the universe is expanding, those waves were redshifted. Remember, when something is redshifted, the wavelength, the length between the waves gets longer. So they used to be of a very hot early universe, but over time, so today, we can do these measurements. You send a spacecraft up there now, you can measure it. Well, the universe has expanded, so those wavelengths have redshifted, right? So remember, a red is a much cooler, has much less energy than a blue. So there's less energy now. They've expanded all the way to the microwave region. That's why it's called the cosmic microwave background. So now it's very cold, and the temperature would be 2.7 K. Remember, Kelvin, K, that's absolute temperature. Temperature can start at 0, right? It can start at 0. So that's evidence. You can just go up there, build a spacecraft, right? Go up there. It's hard to do, but the second one, oh yeah, and then what happened was, they were going, man, those results, let's measure it again. Make sure, because it was the first spacecraft. They go, maybe, so they built another spacecraft, better technologies. They kind of knew what they were looking for now, better. They launched it, did all the measurements all over again, and guess what? It's there. The cosmic microwave background exists, and it looks like a black body curve. The Big Bang. Evidence measurable. Okay, well, let's do a close-up of this so you can see. So let me instead of just looking at me, let me just go on the screen here. Through the magic of cinema. Okay, the Big Bang. And here's those guys in the 60s that first discovered the Big Bang. The theories were out there, but they were the ones who actually detected it using this. So they won Nobel Prizes. They won Nobel Prize in Physics for making, because physics, you win a Nobel Prize, you have to discover things. It's not just like, there was a lot of brilliant scientists who came up with the theories. That was probably actually harder, but it's when you discover something. That's how Nobel Prize works. And then here is data from the Kobe spacecraft. That was the first one that was launched. It went above Earth's atmosphere. It measured, and it's a black body. And the scientist that was in charge of that spacecraft, he won a Nobel Prize for that discovery as well, right? Because that is evidence of the Big Bang, right? And then this just shows that the temperature was 2.7, but there's tiny little bit of fluctuations in it. So it's a little bit, it's where the red is. So this would be a picture of the universe that the spacecraft took. You know, the whole, you know, if you were to look at in all directions where it took measurements, some regions are a little bit warmer than others. You need that. Otherwise, galaxies would never have formed. Everything would have just expanded uniformly, and it would have just expanded and nothing. We wouldn't exist, galaxies wouldn't exist, but there was a little bit of difference in temperatures that allows for gravitational condensation. So if it's a little bit cooler in some areas, and this is ever so slight, I don't know, hundreds of degrees, small. Well, now, so that means that the expansion was slightly different. It wasn't like a perfect uniform ball. It's a little bit lumpy. The universe isn't perfect. There's lumps and stuff. Well, then galaxies could start condensing, gravitational, right? I mean, nothing is perfect, right? So that little bit of lumpiness and things moving around, and then condensation happened, galaxies form, disks form. We all know about that, right? So the Big Bang, it's not just some whiz-bang idea. There's evidence for the Big Bang, right? All right. Cosmic microwave background. It's going to be on the test. So, okay. How do you know about that? So let me go back here. Oh no, now I don't know if I'm going to be showing up in this camera or not. I hope so. Doesn't matter. You can hear me. Don't have to see my face. All right, I hope so. All right, so let's keep going. So let me just check this again. All right, so if I'm here, we'll be fine. All right, so I got my notes. So that is the Big Bang, right? There's evidence for it, measured. You can launch a spacecraft, measure it yourself. It's there. The cosmic microwave background is the shape of a black body, right? If you're going, man, black body, I heard that word. Go look at my videos, read the book. Does a good job, right? Talks about black body radiation, right? You got to know that. So, okay. So the universe is about 13.7 billion years old. All right. So we know from Edwin Hubble, he discovered that the universe is expanding, right? So he discovered that the universe is expanding. Well, let me tell you a little story. So in the 1990s, I was living in Australia, Alice Springs, Australia, right? And I'm in a little gym they have there. It was my break from work. I'm working out, right? This is back in the old days in the 90s. I'm working out, radio's playing, listening to music, working out. And on the news, it said that a scientist discovered that not only is the universe expanding, but that the expansion is accelerating. Meaning it's not just only is it expanding, but it's expanding faster, as though you had your you know, you're cruising at 60 miles an hour, then you step on the gas and you're going 65, 70, 75, 80. I'm like, what? And I'm listening to that, I'm going, man, Australia, pff, this little country, what do they know? They must have got that story. Well, sure enough, it was on the news again, it was on the television news. There was no internet back then, right? So it was just on the news, just radio and TV, that's all you had. And I'm going, this is crazy, it doesn't make any sense. But when a big story like that hits, something like that is going to be measured and remeasured, and people are going to check it, right? Big stories like that are checked and rechecked. Just like similar stories today that are checked and rechecked, right? Do vaccines cause autism? Holy cow, if there's ever been something that has been checked and rechecked by North Americans, by the Europeans, by you know, Japan, China, scientists all over the world have checked the data over and over again. No one's found that vaccines cause autism, right? Something's causing autism. What happens is, of course, is you're young, kids are diagnosed with autism, well, that's when they give them vaccines, right? So correlation isn't causation, not necessarily. Okay, so what happens is that there are these certain types of supernovae, right? Supernovae is when stars have their end of life, and there's a certain type that when they die, when they explode at the end of their life, they know how big this certain type is, they know how bright they're going to be, they're the same, they're always the same, but they're really bright. So when they happen in different galaxies and they see that type of nova, they know how bright it is from measuring ones that are up close. They're able to measure them very good. So if you see something, you know, up close and you've measured the heck out of it, and then you see that thing far away, right? Now it's going to be dimmer, but now you know the inverse square law. Remember that? Remember that from earlier on? So they know how far things are, even though they're far away, because they know how bright that particular phenomenon is when you see it. So anyways, so they use that. And what they found is that the universe is bigger than it should be. These things are too far, they're farther than they should be. So nothing's ever simple in science, nothing's ever simple. Here's what should happen, or here's what they used to think was happening prior to that. So if you had the Big Bang, so the Big Bang was that initial explosion or initial expansion, we'll say. Well, there's gravity, right? So you have this expansion where the Big Bang, right, everything, but then gravity, all the galaxies, all the matter, all the dust, all the gas, it's all attracted to each other. So what everyone thought should happen, there's one of three things should happen. It will expand, but the gravity will slow down the expansion. The gravity will be going, so it's going, but then the gravity's slowing. And one of the possibilities is eventually the gravity will say, okay, and it'll stop, and then it'll come back together. So the opposite of the Big Bang will be the Big Crunch, right? That makes sense. People like that because it means the universe lasts forever. It can just be in this Big Bang, Big Crunch, right? So it's expanding. We know it's expanding. We can measure it. But then gravity should be slowing it down. And then maybe, if gravity's strong enough, if the gravity will pull it back together. Now, but what if the explosion's so big that it's stronger than the gravity? Well, that could happen too. So the other thing is that it should be expanding. It'll still slow down. Gravity will slow down the initial expansion, but then if gravity loses, if the expansion is stronger, then it'll keep expanding, but it shouldn't be accelerating. It should just, gravity will slow it down, but then if gravity isn't strong enough, it'll keep expanding, but then it'll just expand. It'll keep expanding forever. But it shouldn't be going faster. For it to go faster, it's as though either something is pushing it out or there's something outside that's pulling on it. Well, that's weird. What the heck would do that? We don't know of anything like that. So that's where a term, it's hay fever time, right? I'm not allergic to anything, but Northern California, I'm allergic to something, some kind of spore that some plant is doing or something, all right? So, okay. So what's happening though is that gravity is still working. Gravity is still trying to slow down the expansion of the universe, but the universe isn't, so it isn't, although gravity's trying to slow it down, it's not. The universe is expanding, and it's expanding faster, faster, faster. They call that dark energy. Again, dark because you can't see in the dark. So it's energy that we can't see, we can't detect, but we can measure it. Something is either pulling the universe apart faster, 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 or something is, pushing it apart. So it's going faster, faster, faster. It's an enormous force because gravity, all the galaxies still have gravity. Remember, and then the galaxies have dark matter. Remember, dark matter and dark energy are two separate things. Don't get them confused. Remember, dark matter, that's around the galaxies. Galaxies have more gravity than they should. Just because they both start with dark, which is unfortunate. I wish they had different names. But don't get them confused. So there's dark matter, that's matter we can't see, it makes gravity. And then there's dark energy. Dark energy is simply, it's like the opposite of gravity. Gravity wants to pull things together. It'll be an acceleration due to the force of gravity, attractive. Dark energy is a repulsive force that's fighting gravity, and dark energy doesn't work up close. Like this pen, for instance, I let go and gravity's pulling it down. Well, there's no dark energy that's making it go the other way. So dark energy doesn't work locally. It doesn't work in galaxies. It doesn't even work close to galaxies, but it works on this big scales where they see it, where the universe is expanding. And it's expanding faster, 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 and that is called dark energy. And it's been checked and rechecked, and they're pretty darn sure that it's correct. They're pretty darn sure that they're right, that the universe is in fact, not only is it expanding, which we know, but it's expanding faster, faster, faster. So something has got its foot on the gas pedal and it's accelerating up. Let me just look at the camera. Okay, it seems to be recording. Okay. Dark energy, right? Yeah, so my apologies to the Australians when I was listening to a radio and I go, what kind of crazy radio show is this? So I apologize to those Australian radio broadcasters. Apparently they got the story right? So, okay, so yeah, so our normal gravity that we're used to, it's trying to slow down this expansion, but the dark energy is winning. So the universe is expanding, and it's expanding faster, faster, faster. It's crazy. Okay, let me go through some notes. Then I'm going to talk about, oh yeah, so we did the beginning, the Big Bang. Today, we know that the universe is continuing to expand, and not only is it continuing to expand, but it's expanding faster, faster, faster. Well, what does that mean for the future of the universe? Think about that. I'll get back to that in just a bit, right? So let's just talk about some things. Yeah, so cosmic microwave background, that's evidence for the Big Bang, right? Make sure you know that for the test, right? So the expansion of the universe, well, that's the evolution of the universe, right? If it started, evolution is just how have things been going, right? We know, we're used to evolution. We talked about evolution for life, but in order for life to have started, you needed, a planet Earth to exist, right? You got to have a good temperature, and so you needed the evolution of the solar system. But for the solar system to be the way it was, you needed the evolution of the galaxy. And in order for the galaxy to be, the Milky Way galaxy, our galaxy to be in the state that it was, you needed the evolution of the universe. So evolution is just a continuum, right? So the Big Bang and henceforth, that's the evolution of the universe, right? Evolution isn't just life, although it's using those terms a lot. It's evolution of anything. In our case, evolution of the universe, right? And we're here right now. Ta-da! Right? Yeah, and the Big Bang, it's like the birth of the universe, the birth of everything, right? Okay. Now remember dark matter makes gravity just like regular matter. So there's visible matter, that's matter that we can see. I can see this pen, right? It has gravity, susceptible to gravity. I let go and it falls towards the center of the earth. Dark matter makes gravity too. Remember, the galaxies have way more gravity than they should by how much stuff we think is in them. So that matter makes gravity. Both visible and dark matter make gravity. Both of those are working fighting the dark energy, but the dark energy is winning. The universe is expanding as far as anyone's able to tell. So, and it's been checked in reach. So keep all that straight, right? There's two darks. It's just unfortunate, but you'll be fine. You can deal with that. Yeah. Yeah. Okay, so you run that. Yeah, so the universe is expanding, just like a car or a rocket that's going faster, faster, faster. So you know, so you're going 5 miles an hour, you step on the gas, you're going 10, 20, 30, 40. That's acceleration. The universe is accelerating faster, 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 faster. Right? We'll get to that. All right, stuff. I'm just checking some notes here, folks. We'll be with you in a second. Yeah. So if there was no dark energy, what would happen to the universe? Well, it would be like I said. The Big Bang, it's expanding. The gravity would either slow it down, make it stop, it would crunch again, or the gravity would slow it down, and then if the expansion won, well, it would continue to expand, but it would just expand at a slower rate or just expand at a rate. It wouldn't be going faster, faster, faster. So this thing called dark energy, because it's something like that does exist. Some energy exists that we're not able to see, so they call it dark because you can't see in the dark. But if it didn't exist, the expansion of the universe would not be accelerating. It would just be expanding, getting slower, or going at a steady rate, not accelerating outwards, right? All right, about 3.7 billion years old, right? And when was that discovery made? That the expansion of the universe is accelerating. That the universe is expanding, that was in the 1920s, Edwin Hubble. But that the expansion is accelerating, that was in the 90s. You can remember that because where was I? Where was I? I was working out in the gym in Outback, Australia, right? Because I was. I had a job there. All right. Let's talk about let me check my notes. So we talked about the beginning, the middle, where we are now, what's going to happen. Well, the evidence for what's going to happen. What is going to happen with the universe? Well, it's kind of you know, we like cool things to happen. We like to think there's adventure, that there's hope. Afraid not. It looks like it's just going to keep expanding. Now the expansion, the galaxies are not getting bigger. It's just the space between galaxies. This is very important. So the expansion of the universe, the whole universe isn't getting bigger. I'm not getting bigger. The galaxies aren't getting bigger. The galaxies are staying the same size. The space between them is getting bigger. Okay? And we can measure the redshift. Now, although